All right, then let's get started. Welcome everybody to my talk, Bringing Real Cameras to Cycles, Theory and Development of 3D Cameras. So I'll go into what the talk is about shortly, but before that, very quick introduction. So hi, my name is Lukas Stockner. I've worked on cycles for over 10 years now. I think this is my sixth or so talk at the Blender conference, and people are apparently still showing up, so I guess they're not that bad. So I started working on Blender as a hobby, but nowadays I'm doing it as a dev grant from the Blender Foundation, which is, of course, great. Next to that, I'm also working as a platform engineer at a company called Stellia, doing different things there to keep it interesting. And so before that, I've studied physics and computational science, but as you might notice, if you are in one of those areas, I do not have a particular optics or photography background, so if I get any specifics or terminology wrong there, please excuse me. So with that, let us move on to the overview of the talk. What is this going to be about? Cameras, obviously, but before we dive into how cameras actually record an image, we need to discuss what they record in the first place, which is light. So intuitively, this seems very obvious. Well, it just measures how bright the light is, but the whole intensity and brightness topic is not that easy, as you might have experienced if you've ever looked into photometry and radiometry, so we're going to go a bit over that. Then we will look at how cameras have traditionally been done in 3D graphics, so the traditional orthographic, perspective, whatever types. Then, of course, the interesting point, recent developments, the new custom camera type in cycles, what you can do with that, how it works, what the background is, and so on and so on. And then finally, we're going to look at an example of something very cool you can do with that, which was the motivation to do it in the first place. Right, so let's start. We want to measure light. How do we do that? What kind of units? What are we even measuring? Well, at first it seems obvious. Light is a type of energy. It's electromagnetic radiation. So, well, just pick the unit for energy, right? Which would be joule. But there's a problem with that, which is that generally light is fast enough we don't really care about the time aspect. We just look at the steady state. And so, yeah, we want to look at joule per second, which is watt, of course. So easy, done. We're measuring a watt. But it's not that simple. So when people hear watt in the context of lights, they usually think in terms of something like, oh, a 100-watt light bulb. But yeah, it's not that easy, because with the old incandescent bulbs the people used to use, this worked surprisingly well, because they all used the same principle, which is just a black body radiator. They all have pretty much the same temperature, because that's just how material physics works. And so the power that they used was a pretty good indication of how bright they're going to be. But infamously or notoriously, they are very bad at actually producing visible light. So if you put like 100 watts of electricity into a light bulb, it's probably going to produce like 80 watts of radiation technically, but only 2 of those are actually going to be visible light that humans perceive. So now you have the problem if we say, oh, a 100-watt light bulb, well, which watt is it even referring to? And it gets even worse, because if you look at something like a modern LED lamp, on the packaging it might say something like, oh, it's a 10-watt light bulb equivalent to 100 watts, but it still only puts out 2 watts of light. So when we go into cycles now, well, cycles uses watts. That's nice and all. It used to be listed directly as a unit in the property. In recent versions, it's been demoted to the tooltip. So here's a quick poll. Just raise a hand. Who thinks this refers to the electric power? All right. Who thinks it refers to the incandescent equivalent power? Also nobody. And who thinks it refers to the actual light? Well, yeah, of course you're right. Almost, I would say. It's unfortunately still not that easy, for reasons I will go into in a few slides. But yeah, in practice, honestly, it might as well mean nothing, because people just kind of tweak the value until it looks about right, which is unfortunate, because, of course, being able to input real light information would be very useful there. If you actually put in the radiometric watts, what you get is an output in, so you get light watts, and what you get is output in watt per square meter per st-radian. Sounds a bit scary, so we'll go into what that means. So the main problem there, what I said with this whole tweaking values, is that if you work in real units, you have a extremely high dynamic range of realistic values. Like if you have an outdoor scene at nighttime and you have something in direct daylight, there's going to be like a factor of millions or more between that. But in rendering, we want pixel values that are kind of between 0 and 1. Kind of. We have high dynamic range now and so on and so on. But yeah, this is a challenge. So how can we make some sense of this? So with this unit topic, there's two questions now. What on earth is a watt per square meter per steradian? And second, if you actually look at lights, there's all these other units. There's lumen, there's lux, there's candela, there's nit, and yeah, it's just kind of a mess. So what do these mean? Well, you can kind of think of a lamp just floating in a void somewhere, which is outputting light. That was one too far. We've already discussed the total light power coming out of it, which is radiant flux. Technically, by the way, this would be the 80 watts in the previous case, because infrared also counts. But yeah, we need to do more. There's more units around. So if you imagine that we have a sphere around this lamp and it's just illuminated by the lamp, the larger we make it, the dimmer it gets sort of intuitively, because we have this inverse square fall-off that we know from physics. But of course, the radiant flux remains the same. So we need something else to kind of measure this intuitive sense of how bright the sphere is. And so we can say, yeah, if it goes larger, then, well, we just measure watts per area, right? So watts per square meter. And yeah, we can indeed do that. And then we get, if we have twice the radius, we have 4 times the surface area, which means we have a fourth of the watts per square meter. So we have the inverse square rule and everything checks out. So the names for this are irradiance in the context of light arriving at a surface. We have radiosity, which is light leaving a surface. Some of you who've been around for old Blender versions might remember this term, because it's used for a very old and very user-unfriendly way of doing global illumination before we had ray tracing or path tracing. So now you know where that comes from. And technically there's also radiant excitance, which is just light emitted from a surface. So far so good. But now let's think of another example. Let's say we take our lamp and we put a lamp shade around it, which completely blocks the light, so it's sort of like a spotlight now. If we look at the whole thing as a bundle, then the total light power leaving is now less, because we're blocking some of it. But in the directions that we're not blocking, it's still as bright as it was before. So sort of intuitively, we want some power per angle. But angle doesn't really work if we're working in 3D. It's a 2D concept. So what we can, so we need some 3D equivalent of an angle. So what we can do there is, in school, you quickly usually go over what radians are, and then you forget about it again. Quick reminder: you just take a unit circle, you take your angle on it, and you measure the part of the circumference that the angle covers, and that goes from 0 to 2 pi, and that's radians. So we can do the same thing in 3D, but just taking a sphere, taking sort of our cone or whatever of directions out of it, and then measuring the surface area on that. A full sphere is 4 pi, so the full solid angle, as it's called, is 4 pi, and that unit is called steradian. So now you know where that comes from. And if we do that, we get something called radiant intensity, which is just, yeah, power per direction, sort of. And the unit we had, before, of course, combined both of these. So we have, we end up at the sort of fundamental building block, which is radiance, which then locks in both the area and the direction that we're looking at, which means that we're now effectively looking at a light ray, which makes this unit very convenient to work in, because the radiance of a light path stays the same along the ray, which is why it's the native unit for ray tracing, sort of. Technically, there's another variant of each of these when you look into spectral rendering, because then all of them are also per nanometer, but yeah, let's not go there. So there's one remaining issue that we have there. As I said before, 2 watts of visible light, but it's actually 80 watts. How does that work? Of course, the human eye does not see all electromagnetic radiation. We have some sensitivity curve. So we would kind of like to account for that. And so to do this, we can just look at the radiation spectrum, weigh it by this human sensitivity, and then just, well, integrate over that. And that's how we get so-called photometric units instead of the radiometric ones that we had before. To get all of the names of these, you just basically replace radiance with luminance. So you have like luminant intensity and luminous flux and luminance and so on. And that's how you end up with these units that you're probably more familiar with. So what accounting for human sensitivity is lumen, and so on and so on. In the air, for example, nit or candela per square meter is fairly well known from display specifications because, well, that's just how bright the display gets when you look at it. One classic problem is how do you convert between those? So usually you might just Google, what to lumen converter, but the problem there is that since it accounts for the sensitivity, the conversion factor, of course, depends on the spectrum of the light. So technically, the way this is specified is that monochromatic light at 540 terahertz, I believe, which is sort of green, has the maximum sensitivity of 683 lumen per watt, but that's not particularly useful. A more useful value to remember is that so D65, so the standard sort of daylight white that's also used as a reference white in most RGB spaces, has a value of about 180. You will see in a second why this is useful to know. This value is called luminous efficacy, not efficiency. And of course, because it would otherwise still be too easy, there's a second definition of this, which uses the electric power that goes into the lamp. So yeah, it's a bit of a mess. Right, conversion depends on spectrum. So with all this out of the way, let's look at cycles lamp units. What do we use? Well, we said we use watts, but it's not that easy. Point lamp, very simple, we have watts. Area lamp, also simple, we have watts. But then it starts to get weird. So what do I mean when I say a spot lamp has watt per steradian times 4 pi? What it means is that to keep it convenient for the user, it's designed so that when you change the angle size, the actual radiant intensity remains the same. So basically the value that you enter is, if this was a point lamp and there was no occlusion going on, how many watts would it have? Which is a bit weird, but well, it's weird in terms of units, but it's convenient for the user. Since most users don't care about units in the first place, it's arguably the best pick. Then we have the sun lamp. So this just puts out a fixed intensity, which means that the larger you make the scene, the more energy arrives, so it can't really be watts, which is why sun lamp is watts per square meter, so irradiance. Then we move on to the emission shader on surfaces. This is measured directly in radians because, well, it's just, again, convenient for the user if the pixel value ends up being exactly what you type in. And since we work in radians, well, that's how it works. This also means that, for example, if you have a plane and you want it to work as an emitter that has the same intensity as an area lamp, you need to take the value in the area lamp, divide it by the area, and then divide it by pi to get rid of the steradian factor. It is what it is, unfortunately. And yes, it's pi, not 2 pi. The stuff is weird. Then we have the background texture, which works just like emission. You just directly get your pixel value, so it's also radiance. And conveniently, the sky texture outputs the same. This actually outputs physically correct units, like not just some fantasy factor on top, which is why it usually appears way too bright if you put it into the scene and you need to reduce the strength first. And the RES texture is, again, somewhat unfortunate because RES files contain the light intensity in photometric units. So to convert this for cycles, we need to assume some kind of luminous efficacy. So we just use these 180 there, and well, if the lamp is not white in terms of D65, then, well, it's just wrong. But unfortunately, that's how it is. Luckily, there is now a chance to fix this because in recent versions, I'm not sure if it's 5.0 or if it's also 4.5, there now is a color temperature input. So technically, it would be feasible to automatically compute this conversion factor as long as you have a black body temperature. If you make your lamp pink, that's not going to help you. But at least that's something. So there is, I would say, a reasonable chance that this situation will improve at some point. But yeah, not quite there yet. Right. So I said all of this is unfortunate, and usually people just tweak the values. But of course, this is not a problem for real cameras, right? There you have your classic exposure triangle, you have an F number, you have your exposure time and ISO. And if you set those right for a given scene, then it's probably going to come out right, assuming neither you nor the camera manufacturer messed up. So given these values, so if we have these values from a real camera and we have the real-life light intensity, can we somehow set up cycles so that we get the realistic exposure that corresponds to that? To do that, The interesting factor here is the ISO, because it's basically just a proportionality term that was thrown into there, because, well, f number and exposure time is kind of fixed, and ISO is just the magic glue that ties it to the exposure. So you can look up the definition for this, and you get this wonderful formula, where n is the f number, t is the exposure time, s is the ISO sensitivity, L is the average seen luminance, photometric units, unfortunate for us, and K is a calibration constant, which the standard says has no fixed value. It's up to the manufacturer, which is very lovely, and so different cameras use different standards here, but a common value is 12.5. And so if we have all of our camera settings, this tells us the average seen luminance that should be well exposed with these settings. So we can work with this, but to find what we should set our exposure multiplier to in cycles, we need to A, somehow deal with this luminance to radiance factor, and B, we need to know, well, now we know which physical unit is well exposed, but what does well exposed mean in terms of pixel value? So what are we trying to scale it to? For a quick and dirty approach, I would say just assume the white point of D65 to convert from luminance to radiance. So we have again our factor of 180 or 177 to be exact. And for the target pixel value, I mean, I guess you could argue several values. You could argue, oh, it should be 0.18 because that's middle gray or something. But honestly, I would just put 1.0 because nowadays we have, okay, I'm seeing headshake. Again, I'm not an expert. My argument would basically be we have tone mapping afterwards anyways, but I don't know. In the end, it's just artistic. Like, tweak the value until it looks good. But yeah, just to sum it up, so this is what you would compute to get this factor that you put into the film exposure. And if you do that, for example, there's this Sunny 16 rule in photography where you just set the aperture to f16 and you set the exposure time as the inverse of ISO, and then you should get a reasonable exposure at daylight. And if we do the math for that, it comes out to 0.055. And if you do put that as the strength for sky texture, you actually get a reasonably exposed image. So it's nice when things sometimes work out. And to be completely honest with you, that's how I arrived at this 1.0 value. I figured out what value I need to set to make it look good, and then it turned out to work with 1.0. So, right, but that's enough of light. This is a camera talk, so let's move over to the cameras. How do cameras in 3D graphics traditionally work? So, if you look at this from a rasterization or OpenGL, DirectX, whatever background, the traditional setup you have is that there's 3D matrices called model, view, and projection. The idea there is that if you have 3 matrices, you can multiply them together, and it just becomes one in hardware. So this is super efficient for the early cards that where multiplying numbers with one matrix was actually expensive. So traditionally, the way these are used is that you have your model matrix, which moves the points from local coordinates to global coordinates, which is useful because that way you can do instancing without changing the actual geometry data. You just change the model matrix. Then you have a view matrix, which moves things so that the global coordinates are mapped to camera coordinates, which is basically the same thing, except that it pretends that the camera is at the origin and facing in a defined direction, usually Z. And then after that, you have your projection matrix, which maps 3D coordinates from which maps 3D coordinates to screen coordinates. So then your x and y is actually x and y on the screen, and you still get z, which is used for the depth buffer. For orthographic cameras, it's fairly simple. It's just a bunch of scaling and translation. For perspective cameras, it's not immediately obvious how you would get actual perspective out of a linear operation here. Well, in the background, it's not a linear operation. There's a perspective divide and so on, but let's not get into that. So yeah, traditionally, this is how you just program cameras in your 3D engine or whatever. Nowadays, we have vertex shaders, so we can get a lot more creative here. This is no longer done in hardware. So you might think, oh, we can now just implement any camera by translating our vertices accordingly, but that's not the case, because one fundamental assumption in rasterization is that straight lines in 3D must remain straight in 2D, because that way you can just take your vertices of your triangle, transform those to the screen, and then you end up with a 2D triangle that you can fill in. If that's not the case, you would need to check individually for each pixel, and then you're basically doing ray tracing anyways. So traditionally, that was a limitation on camera types, and this is also why, for example, the panorama camera does not work in the Blender viewport unless you switch to cycles, because, well, the only way to do it would be to render to rasterize and some other camera projection and then kind of remap it afterwards, which is not great. But luckily, this is a cycles talk, so we can look at how cameras work in ray tracing, and there we have much more flexibility. Basically, we just take in a position on the screen and some other information like lens samples and time for motion blur and whatever, and stereo camera information. And then we need to output a ray with origin and direction that represents, well, what should be traced in the renderer to generate the color for this pixel. For orthographic cameras, this is very straightforward. You can just imagine a floating virtual screen. We pick the position on that based on the pixel we are currently rendering. The direction is always the same, namely what the camera is facing in. And then we just generate arrays, which are the blue arrows here. For perspective camera, it's very similar. There we again have the floating screen and pick a position on it. But now we take a ray by we generate the ray by taking the position of the camera and connecting it to this virtual screen, and then just normalizing that and using it as the direction. Of course, the distance between those two then affects the field of view and so on, but conceptually this is fairly straightforward. But with ray tracing, we can now also do things that rasterization couldn't do, such as accurate depth of field. How does this work in real cameras? Well, up here we have an example of a real camera. So we have a sensor back here, and this is subdivided into pixels. So here would be, for example, 5 pixels. And each of those is, of course, a physical sensor. So light arrives at it from any direction. It just sums it all up. So these 5 rays illustrate 5 different directions from which the light might come. And then we have a lens in front. Here it's very simple, just one lens. Of course, in practice, you would have many more. More on that later. And so this shows that light from many different directions can end up on the same pixel. And if everything is going well and you're in your focal plane, then, well, this one pixel maps to one spot and everything is sharp. But if your object is somewhere over here, you're going to see many different areas of the object blend together into one pixel, and that's where your depth of field comes from. In 3D cameras, we usually don't explicitly model this lens and everything. Instead, we use a trick, which is, well, we know from the definition that at the focal point, everything comes together. So we can just start with our regular blue ray, which is generated with this. Then we trace it against our focal plane, so we get this point. And then we have this green thing here, which is the aperture or the pupil of the camera lens. In this context, it's the same. So you just set the size of this by inputting your F number. And we just pick a random point on this, and then we connect it to this point because, well, we know no matter where we start out here, we must end up in the same point in the focal plane. And then we just take the green arrow as the ray that we are tracing instead. And this is how you get depth of field in a path tracer. And yeah, it works surprisingly well. Of course, the real perspective camera implementation in cycles has a lot of additional details to it. You need to account for motion blur. You need to account for stereo projections, you need to account for the shift that you can do with a sensor, but overall, that's the idea. Right, and then as mentioned, of course, we also have these panorama cameras that traditional renderers couldn't do. This is basically a collection for everything that doesn't preserve straight lines. As you can see in this example here, this is one of the world backgrounds bundle in Blender. The lines are very obviously not straight. There's all sorts of models in here. We've got fisheye lenses, we've got equirectangular, which is this one, and so on. But over time in cycles, this sort of became like a dumping ground for all of the weird camera models that don't really fit into the other two categories. And at some point, this started to become a problem because there's many things that we could add there and that would be good to have. Like, for example, obvious candidate would be lens distortion. So real cameras also don't preserve straight lines. You've got some barrel or pincushion or higher order distortion in there. That's important, for example, in VFX. If you're matching your rendered footage to your real footage, then the distortion should match or it will stand out. Currently, people usually do this by calibrating the real lenses to get the distortion, and then warping the rendered footage in the compositor. But of course, warping is not perfect because you lose some resolution. So it would be nicer if we could account for this during rendering and already render the distorted footage.
Actually, usually people undistort the images from the camera and then combine them and then distort.
Oh, okay. That's even worse because then you lose the resolution twice. So yeah, it would be nice to do this in rendering, and the obvious candidate would be, well, just use the lens distortion model that we have in Blender, right? But last Blender conference, I talked to some people who are on VFX, and I was told, oh no, there's like a dozen different models that different camera software implement, and ideally we would have all of them. So this is starting to get a problem, and it doesn't quite scale anymore. Right. So for a long time now, the idea has been floating around. We would somehow like cameras to be more flexible. We would like to allow people to define things like their own aperture shapes and just generally all sorts of things. Because that way we don't need to implement everything, right? We've got these lens distortion models that I mentioned. At one point last year, we got a pull request to add a model called Fisheye 624, which is used for some VR and AR headset, which is, of course, a reasonable proposal. That's something we could add, but it also adds 14 parameters, and if you look at the code, that turns very ugly very fast, and if we add that, there's probably going to be like 5 additional models that we should add. Then there's other panorama models, like for example, we did add the central cylindrical camera, which is used, for example, to generate prints for interactive exhibits. So you can sort of just print it out and roll it up into a cylinder, and you can walk inside, and then it sort of looks like a 360-degree panorama, which again is useful, and we did add it because this one was not too complicated. But it is fairly niche, and if we just keep adding all of this stuff, there are real concerns about complexity of the Cycles code, and so Cycles GPU code is already orders of magnitude more complex than what most people do on like GPU processing, and we already regularly run into compiler issues or limitations because, well, other people just don't do this sort of thing, so it's always a struggle to try to keep it as simple as possible and not have like 500 different camera models in there. And finally, the big one that I was talking to several people at the last conference was being able to model realistic lenses. So there's this plugin for the Arnold renderer called Lentil, which a lot of people use, and a lot of people, when you bring it up, would be, oh, this would be so amazing to have in Blender. But yeah, again, adding this, there's some problems to it. More on that in a second. And again, there's many other things. Like on Wednesday, there was a very interesting talk. I would highly recommend you check it out if you haven't seen it, about simulating real lens systems, also in terms of path tracing or ray tracing through the lens, which is something, you know, that we could absolutely do in Cycles, and it would be very cool to have. But then you need all this code to define the lenses and so on. There's the classic topic, custom aperture or bokeh shapes. So in real life, people sometimes do cutouts from post-it notes and put it in the front of the lens to get the custom bokeh. Could absolutely be done in Cycles, but again, we can't really do everything. So at some point, it would be great to give the user some more flexibility there. And if you think about it, the interface between the camera and the rest of the renderer is really simple. You don't need crazy deep integration like you need with shading models, for example. It's really just a case of camera position in, ray out. That's it. So how can we make this work? In Blender, the obvious candidate would be nodes, but that would be a ton of work to implement, and realistically, good luck implementing ray tracing through real lenses in a node system. I know there are people out there who could do it. People do crazy things with nodes, but it's not exactly the peak of user-friendliness, I would say. And so in the context of this realistic lenses, again, more in a second, one topic that came up was, could we do some form of just-in-time compilation to also get the nice performance going? And, well, while thinking about that, after a few days on the train ride to the airport, I had an idea, wait a second, we already have an entire just-in-time compilation solution in Cycles, which is OSL, Open Shading Language. So the idea with OSL, of course, is that you can write your shaders for the material in there and then output like diffuse and glossy BSDF or whatever, and then Cycles takes care of rendering that for you. And that's really what it was designed for and intended to do. But realistically, it's also just a programming language with a just-in-time compiler backend on it. And it is flexible enough to not only output like material data, but arbitrary data, which was, again, intended, for example, for things like displacement, because there you just need to output a height value. But in theory, there's nothing stopping us from just pretending, hey, this is totally a shader, take this, input these few values, take a few values out, and then we just pretend that these values are origin and direction for array, right? So OSL does actually have a generic type called shader, which is different from the surface that you would use for a shader. Terminology is a bit weird, sorry about that. So yeah, we can just take this generic shader and, well, pretend that it's a shader and use it as a camera. Of course, there's some weirdness there, because since OSL was not designed for this, there's a ton of built-in functionality that ends up not really working, like what is a UV coordinate in the context of a camera, or what does it mean to look at are we back-facing or not in the context of a camera. So if you try to do that, you just get usually 0 back. But well, this works. And later on, from talking to the OSL developers, because there was one bug that we needed fixed, it turns out we're not even the first ones to do this. So Octane, I believe, also supports this, and apparently a number of in-house renderers are doing the same thing, to the point where they are actually considering adding a official camera shader type. So that's pretty neat that everybody comes up with the same solution. That's usually a good sign that this is in fact a reasonable solution. Of course, it's not entirely perfect that you need to write code for this. Usually we try to keep things to nodes or whatever, but honestly, building your own camera is a fairly advanced topic anyways, and not that many people are going to do it. And if somebody does it, you can probably expect some level of like being technical. So I think this is a reasonable choice. The advantage is that this gives us the full flexibility of a real programming language. Like if you put a color palette somewhere in the scene, you could theoretically write a camera that runs Doom. So that's pretty neat. And as I'll mention later, there are genuine use cases where you need some complexity in this. We get great performance because all of this goes through the LLVM compiler backend. So you get actual machine code out of there that's properly optimized, can make use of vectorization, and so on and so on. And it allows us to reuse the entire OSL ecosystem, which means mundane but important things like, support in code editors, support for syntax highlighting, that sort of thing. It's more useful than you might think at first glance. One important thing that I need to stress here, because that was generally the main concern when I talked about this to people, is, oh, but OSL is slow, isn't it? Well, kind of. So it's not really the fault of OSL, but OSL in cycles has a reputation for being slow for various more or less complicated reasons. But the important thing here is that the whole camera thing is completely independent of shading. You can use this without enabling the OSL checkbox. So you can continue to use your nice, fast SVM shaders and still use this in the background. And the performance concerns that OSL has in shading do not apply here. So we get quite lucky there. Right, so let's look at a quick example. What does a camera look like? So this is an example that's actually bundled in a text editor in Blender. We have two in there, the basic and the advanced camera. This implements a basic perspective camera. So what we do here is we get in a parameter called focal length. So this is then displayed in the camera properties if you load this up in Blender. And then we define three outputs called position, direction, and throughput. These names are fixed. They have to be called like that because that's how Cycles picks up the data. And then what we do is we use this get attribute, which is again some OSL internals. So we can query an attribute called sensor size. This is the size of the camera sensor that you define in Blender. There's a good chance you haven't looked at this before because for the virtual cameras that we usually use in rendering, sensor size is kind of meaningless. It's basically just used as a proportionality constant for if you enter an actual focal length in millimeter. But with the real cameras, it starts to become very, very relevant. Then we have this built in here called camera shader raster position, which gives us 2D position between 0 and 1, which is just where are we in the image. Then we normalize this by subtracting the midpoint from it. Then we multiply this by the sensor size and divide it by the focal length. And surprisingly, this is all you need to implement a perspective camera. So then we can just take the X and Y coordinates here, take a fixed distance, this is the virtual image plane that I mentioned, normalize the vector, and we get the outgoing direction. We don't even need to touch the position because it just defaults to 0, and that's our origin and camera coordinates. This is all in camera coordinates, so if you move the camera around, you don't need to explicitly account for that in the shader. And that's all there is to it. If you run this, you get a perspective camera that does pretty much the same thing as a basic perspective camera in cycles, which is not super exciting if you're a user, but it is very exciting, let me tell you, when you implemented this and it works for the first time. All right, so here's the advanced camera example. So this does a few things just to play around and show what's possible. So we start here in the same way. We get the raster position. Then here what I do is I apply this lens distortion. I did not include invert distortion model. This one is a bit unfortunate because most of the distortion models are defined in the wrong way around for what we're doing here. So they map the other way, which means that we need to do numerical root finding in here. So this invert distortion model is like a Newton solver. But yeah, you can look at it in the Blender text editor if you're curious. So yeah, we just get this distortion factor here and then multiply a value with it. Then the next thing we do here is again this perspective operation, same as before. Then again, just to mess around here, I do some Perlin noise and add it to the point so you can get the nice swirly magic effect in the camera. Again, something you could never do without post-processing and rasterization. Then we normalize again. And then finally here we have this depth of field operation that I mentioned before. For convenience, you can get the focal distance value from the standard Blender camera. So you don't need to pass this in as your own parameter. And then you just, do this computation here. Here, this is also important, this aperture position. This gives you a different value every time because this uses cycles built-in logic to sample the aperture. So this respects like the F number that you configure in Blender and so on. And in the future, also, for example, if you set a polygonal aperture, well, this is going to respect it. Right, then we apply that and we have our direction. Here you can also see, you can apply these attributes to these input parameters, and that's how you sort of define how they are exposed in the user interface. For example, OSL does not have booleans, it only has integers, but if you say widget is checkbox, then this is displayed as a checkbox and you just get 0 or 1. For example, sensitivity tells you how much the value changes if you drag in the UI, and that sort of thing. There's a ton of these. The only one that we don't currently support at the moment is the one that changes the label for it in the user interface because there's some internal limitations on changing the display label of custom properties. But right, so that's an OSL camera. So what are the limitations of this at the moment? There are unfortunately a few. First of all, there is no inverse mapping. So in addition to the get array from a screen position, all of the built-in cameras and cycles also support the opposite. Give an array, find what position on the screen this corresponds to. We need that to do two things. First of all, there's the vector pass, where you get the information on how much a pixel has moved since the previous and last frame. The way this is done is, of course, taking the previous and next position and mapping back to the camera. Can't do that here. And also the window texture coordinates. In theory, we could just let users specify a second OSL program that does it the other way around, but probably this vector pass and texture coordinates are niche enough that so far this hasn't really seemed worth it yet. Then the second point that's of course a concern is OSL is currently not supported on HIP, Sickle, and Metal. So HIP is AMD hardware GPUs, Sickle is Intel GPUs, Metal is of course Apple. Would very much like to support this, but realistically, porting OSL to one of these backends is not something that we can do. It started out on CPU. NVIDIA eventually ported it to optics, but those, someone from the vendors is listening, please do this, would be very cool. And then two easy ones. Right now, there's no way to do your own stereo, like stereoscopy implementation. It would be very straightforward to just pass in, hey, which view are you? Are you left or right eye? And then the OSL code can do its own thing. And then if the shader accepts this as an input, we don't do our own stereo logic. Planned, I just didn't get to it yet. Another obvious one, just put in the time parameters. You can do your own custom motion blur. And then the last one that might get some people very excited if I spell it out like this, no spectral effects yet. So spectral rendering in cycles has always been this big dream. There's many reasons why it's not here yet, but there's one thing that's coming, hopefully soon, and that is dispersion support. I'm currently working on that. Pull request is open, not quite ready yet. So the idea there is that rays start out as usual, but as soon as you hit a glass object or some object with dispersion on it, you pick a random wavelength, you adjust the throughput of the path to account for that, and then you, adjust the index of refraction based on the dispersion parameter. And the important thing is we remember this wavelength so that all future bounces of this path use the same one, because otherwise it's not correct. So the idea is, if we want to have a camera that does, for example, dispersion, we could make it so the camera can say, hey, I would like to have a wavelength input, please. And then we do this right from the start, give the camera a wavelength, and then use the same for all the dispersions calculations internally. The downside of this is you get color noise, so you need a few more samples to get rid of that. But, that's a fine price to pay if you get reasonable distortion out of it in many cases. Should hopefully also get this soon. And another corner case, just as an example for the sort of thing you can get into when you implement things like this in a production renderer, volumes. So when you trace a ray through a volume or a path through a volume, you need to know which volume you're in at any given moment. That's fairly easy at first. If you hit the volume from the outside, you just add it to your stack and you're done. But what if your camera is inside a volume to begin with? Then you need to initialize the stack correctly. So the way we do this for regular cameras is just we take the camera position, we trace a ray one time before we start rendering, we trace a ray towards the world, and we just count up, hey, which volumes are we leaving? And then, the camera is in those, obviously. But the problem with the OSL camera is you can do anything. You could, in theory, write a camera that claims to be at the origin, but starts its rays 10 meters over there, and then all of the values are going to be wrong. So there's not really a proper way to fix this. The honest answer is just, if you want this to be correct, don't mess with the origin. It's an unfortunate answer, but, it's just how these things sometimes interact with each other. Right, but now to the interesting part, which is modeling real camera lenses. This would be a very, very cool thing to do, because there are many effects in real cameras that are not currently represented by these virtual cameras that we have in cycles. Fancy bokeh effects are classic. There's this cat eye effect that you get different bokeh shapes on the outside of the lens. You will see that later. You get lens distortion, already mentioned. You get vignetting, which you can do in post-processing, but it would be nice to have it sort of natively. You can do dispersion and so on. Again, I'm not a photographer. I'm sure photographers will be able to talk for hours about the amazing things you can do with historic lenses or whatever. I just have to believe them. Another factor, of course, is this allows you to match what real lenses do. So again, this is super valuable for VFX if you can use literally the same lens for your rendering. It can be useful for research, like if you're designing a lens, you might want to visualize, hey, what is this actually going to look like in practice before I manufacture the thing? And, it just allows you to have a list of neat looks that you can go through and say, yeah, I like how this lens looks, I want my render to look like this. Now, as we've seen in the talk on Wednesday, you can trace rays from the sensor through the lens setup, and that works reasonably well. But there are some problems with it. First of all, there's of course a performance problem. Tracing rays is not cheap. It's not free. So we need to account for that. If you're doing some research application, you just wait a bit longer. But if it's just a case of I want a neat look, are you really gonna pay 50% render time just to get that neat look? And a second problem is if you have a small aperture, this starts to get very inefficient. Because, for example, if your camera is set to f16, then something like 99% of rays are just going to start from the sensor, go through the lenses, hit the aperture, and get blocked. And only 1% is actually going to make it out of the lens. So performance overhead starts to become a lot larger at that point. And there's some other problems that are not super important for us, but that do come up in the papers if you look at this. For example, there's no obvious way to do inverse mapping, which is relevant for bidirectional rendering, for example. You could, in theory, just trace the other way, but if you're accounting for reflections, you might not end up with the result that you want. So instead of doing this explicit ray tracing, can we approximate this somehow? Yes, we can. So there's this concept called ray transfer matrices, which has been around for a very, very, very long time in optics theory. The idea there is that you can represent your path as a position and direction. So usually again, not an optics person. What people do here, from my understanding, is that you do a so-called small angle approximation, which is that you say, oh, the sine of x is kind of equivalent to x if x just stays small enough, and then you can get rid of a lot of trigonometry in your equations, and things get a lot more linear. Usually also, if you look at this in the optics literature, it's in a 1D context, so you just say we have one position in one direction because lenses are kind of rotationally symmetric. In practice, they are not really. You often have also things like cylindrical elements. So in our context here, we are talking 2D, so we have two positions in two directions. And then the idea is that we can just represent points or rays as vectors, and we can represent optical elements or things along the optical path as matrices. And then the idea is we can just multiply all these matrices together to sort of describe what this optical system does to our rays. So for example, here you see an example, a ray going in and going out, and then this is the ray transfer matrix for an ideal thin lens. In this framework, ideal lenses are linear. Real lenses aren't, of course, but it's neat to have this as a fallback because it means that if the approximation of the higher order terms is not exact, then at least we're going to fall back to something that's at least sort of correct, and we only have some higher order terms not represented perfectly instead of a completely messed up image. And another advantage that will come in later is that free space is linear in this context, which means that if we just have a gap in our lenses, we can very simply jump forward and not have any approximation error in there. So having these linear models as a starting point is nice, but for real lenses, this is, of course, way too restrictive. If it was a linear model, then it would just be a projection matrix, and we would be back at where we started with our real-time graphics. So, well, if we need higher order terms, can we just use a polynomial fit to real lens data? The answer is kind of, but not really. In theory, this could work, but the problem is that to represent real lenses, you need very high order coefficients, like something to the 10th power. And because we have 4 input values here, really 5, because you also need to account for wavelength to do dispersion, you get a combinatorial explosion, and you would have millions of parameters at some point in your polynomial. So trying to fit that, good luck. But luckily, there's 2 great papers here to address this concept. It's efficient Monte Carlo rendering with realistic lenses. Sounds very good for what we want to do. And sparse high-degree polynomials for wide-angle lenses by Emanuel Schade, Johannes Hannecker, and Carsten Doxbacher. So the idea that they have is you start with a lens system that's usually described in terms of, a list of optical surfaces. You know where your the size of your sensor, you know the definitions of the lenses, you know the radius of the lens body, and so on and so on. Then you trace a lot of rays through this lens, like hundreds of thousands, millions, something like that. I think they use around 100,000 in their implementation. And then you fit sparse polynomials to this data. So the idea is you have 5 input values, which is direction in 2D, position in 2D, and wavelength. And you have 5 output values, which again are position and direction of the outgoing ray, and throughput to represent light being lost through reflections or whatever internally. And then the idea is that you can just use this in your renderer. So here you see we have 2 polynomials. We have one that goes between sensor and aperture rays, and one that goes between sensor and pupil rays. So here's a very simplified real lens where you have a sensor, you have your aperture in the middle, you have your pupil outside, and then you have optical elements between those. And you have a closed sensor body here because, for example, if a ray goes too far to the side, we want to actually cut it off instead of just letting it escape because, well, it's a realistic lens, right? So then to use these polynomials in a renderer, of course, you need to get them in there somewhere. The way the reference implementation does this is it just generates a C code for a given lens. And then if you want your program to support 10 lenses, you just have a big switch statement in there and you copy-paste the code blocks for these 10 lenses. That's also how the Lentil plugin does it, for example. But it's not really great for what we want to do here, because if you want to add a new lens, you have to recompile the entire code base, which is unfortunate. I tried to get around this by doing a simple bytecode VM, which basically just has 3 instructions that you need to evaluate polynomials. The idea would have been, just generate this intermediate bytecode representation from the polynomial and load that into cycles. Problem is, it's about 20 times slower, so that's a no-starter. And this is where the whole just-in-time compilation thing came from earlier, which led to the OSL camera and so on, that I was thinking about how the hell can I do this, and then, oh, we can use OSL, and that also solves all the other problems. Nice. Right, so how does this actually look in a renderer? There's two approaches, sort of. You have the naive approach, which is you start on the sensor somewhere, you know the position on the sensor from the pixel you're rendering, you pick a random outgoing direction, you evaluate the polynomial to find out what your aperture position is, you check, did I hit the opening, or is the ray being blocked? If it's blocked, we just discard it. If not, we evaluate the second polynomial to find our position and direction on the pupil. Again, we check if we hit the sensor body or whatever, but if we actually hit the pupil of the lens, then we say, okay, nice, and we use the origin and direction as the ray that we are tracing. But if we do this, we have the same problem that we had before, which is that most of the rays will just not hit the opening in the aperture, and we have a lot of inefficiency. So we can be smarter about this by picking a position on the sensor, picking a known valid position on the aperture, and then working backwards. So doing, again, root solver on this sensor to aperture polynomial to do it the other way around and find, okay, which outgoing direction do I need on the sensor in order to hit this aperture position? Once we have that, we can then take sensor position and direction, evaluate the other polynomial to get to the pupil. There we again need to check because, well, we can't do two backward steps. But if that is fine, we can just use this ray. And that way, it doesn't matter how small or large the aperture is, we always hit it. Or aperture we always hit, pupil can still get in the way, but practice that turns out to not be a huge problem. One theoretical note here, from what I understand, this is theoretically not exact as it's implemented in Lentil and currently also in my example, because the problem with this approach is you just sort of assume that all aperture positions are equally likely. In practice, that may very well not be the case. So what you should do is to account for this with Jacobian terms, etc., in the probability term. But honestly, doing so is quite complex. And I mean, Lentil doesn't, and people haven't complained, and they still love it. So I guess it's just fine to not do it. Will be something to evaluate at some point in the future. One theoretical note on this also. We want to be able to adjust focal distance for depth of field. In the theoretical cameras we have, this is very straightforward because we fake it all anyway, so we can just compute this. In real lenses, of course, the way you do this is that mechanically speaking, usually you have some fixed and some free lenses, and you know if you change the focus, some parts move. How can we represent this here? We could do this by splitting it again and saying, okay, we have one polynomial for the fixed part and one polynomial for the moving part, and then we have a free space in between. Turns out there's an easier way. You get the equivalent result if you just move the sensor a bit back or forth. Real cameras don't do this because mechanically it's very complex, but this isn't a real camera, so we can just do that, and that makes the computation a lot easier. That's also one thing that they do in these papers. The downside is that you need to pre-compute how far do I need to move the sensor to get a specific focal distance. And it's not that simple because the entire concept of one focal distance is not really uniquely defined for a real lens. You might have some wonky focal plane, you might have aberrations and so on. So in practice it's not exact, but usually it works reasonably well. So let's look at a quick example here to wrap this up. We can take this lens, which is one of the examples provided in the reference implementation of these papers. We can take an example scene, for example this one. You might have seen this if you looked at the pull request for the custom camera, in which case the result is not going to surprise you. So this is just how it looks with the basic camera in cycles right now, just some depth of field and so on. And we now take this lens, which looks like this in real life. Again, credit to the paper authors for this graphic. We get a render that looks like this. Not immediately different, but if I switch back and forth, you can see that there's quite the difference here. So for example, the flower looks basically identical because, well, it's... okay. The flower looks basically identical, but at the borders, you can see that things shift slightly. You get the vignetting effect. You get a weaker depth of field, interestingly enough, or seemingly more focused towards the outer edges, and so on and so on. So you get really this realistic lens behavior. Also, funnily enough, if you just change the sensor size in Blender, you eventually get to the point where you just have a small bright spot in the middle and everything else is black. Because again, if you really in a real camera, if you just make the sensor bigger, well, that's a perfectly realistic result. And just for a quick illustration of where this apparent sharpening on the outside comes from, this is the bokeh effect you get with the built-in camera in Blender if you just have small emitters and you defocus them. And again, with the same lens, we get this render. So the effect you see here is that the pupil starts to occlude some of the rays towards the outside, which is why it gets darker, because just less light makes it through. That's where the vignetting comes from. And also because the bokeh is smaller, it appears sharper. So yeah, it's cool to see this actually work, and I was again very happy when I saw this for the first time. So what is the current status of all of this? We have the custom camera, of course, so you can use that right now. You can use it for, I believe, 2 versions already. In my pull request for this, there is an example for this lens that I just showed. I will update it afterwards because the example is quite old and doesn't work with the version that was actually merged, but I have a working one and will update that soon. I have locally the code to perform these lens pre-computations. So for a given lens, you can generate the values that you then put into your OSL script, but that needs a lot of cleanup because, well, it's just reference implementation from the researchers, which is already a bit funky, and then I made a lot of changes to it. So it's not in a good state right now. And there's a lot of open usability questions for actually making this practical. For example, things like file formats. Ideally, people would be able to exchange lenses in a standardized way. Ideally, even manufacturers could publish data for these lenses. Ideally, you could use them even in other renderers, and just a lot of things like that need to be considered in the long term. And honestly, it's also an open question how much of this should actually be part of cycles natively versus how much should we just provide the infrastructure to be able to build things like this and then leave it to extensions and the community there. So that's always a tricky trade-off. There's one more thing that I didn't even list here, but that I'm currently looking into. No promises or anything, but maybe it works out, we'll see. There's one other thing that this lentil add-on does that a lot of people like, which is that it optimizes the noise for bokeh effects. So right now you have the problem this often ends up being very noisy if it's a tiny highlight. And because the chance to randomly sample the outgoing direction that will end up hitting this bright spot is very low. So what they do there is a sort of almost bidirectional approach where you trace normally, but if you find a very bright path, you then go backwards and say, hey, can I find another position on the lens, and try to somehow connect that to the same path, because that way, instead of getting one super bright highlight somewhere, I could spread it out over like 16 pixels, and that way the noise ends up being a lot lower. So if you look at this from a theoretical point of view, it's very complex to do this accurately. There's all sorts of reciprocity, I think you pronounce it, considerations that you need to account for. You have probability factors. How likely would it have been to sample this path the other way? There's, of course, the possibility the other path is occluded, so you need to do a ray test. Reflectivity of the first object you hit changed because you're now coming from a different direction, and so on and so on and so on. In practice, you can probably skip a lot of this. Occlusion, I think, is very important, but the others, for bokeh, we can probably just get away with assuming that it's the same. Still not very easy to implement in cycles because of how we do the GPU tracing. It's all done with a sort of so-called wavefront architecture. So by the time we actually hit the light, we've forgotten all about the camera information and we just know which pixel this belongs to. So we would need to remember at least some information so that when we hit the light, we can work backwards and generate these additional rays. But remembering additional information is always costly because there's potentially millions of rays active at the same time. So if you add one single floating point number, that's 4 megabytes of GPU RAM that's gone. And so, yeah, that's always something you need to trade off. And then there's also problems when you have these fractional samples, sort of how does that integrate with adaptive sampling? And yeah, production renders are not that simple sometimes, but it might end up being doable, and if it is, you'll see more, hopefully soon. And with that, thank you for your attention. I hope it was interesting. And, yeah. All right. Yeah.
Amazing physics tutorial.
Thank
Thank you.
you.
How would it from production point of view? Does it support normal class, world position class, 3D?
Yes, all of that works. Yeah.
Fantastic.
Of course, if you have something like that for field, you're going to end up with noise in there, but well, that's already the case. The only thing that's not working is vector pass. Right.